So we're ready to go. Good morning still, I guess. So I'm going to talk about another one of the big draws to CP2K. So I think we've heard about the GPW method, which is this nice method with some fairly favourable scaling characteristics that allows to tackle fairly large systems. And Jörg also talked about the fact there's quite a lot of functionality for moving the atoms once you've calculated the energies and forces. And there's a lot of MD features, particularly compared to other DFT codes. Marcella's talked about the GAPW method, so you can tackle all electron problems. And she hinted at the end that you can do a lot of spectroscopy and stuff. We've not had time to go into lots of details, but if you ask Marcella about that, she'll tell you lots of things. There's another set of things that CP2K does rather well. I mean, it does many things, but this is one of the things it does well, which is to calculate using so-called hybrid functionals. Those of you that do DFT regularly may notice in many journals that there's a transition away from so-called GGA or semi-local functionals, and there's an increasing trend that people will use something that goes beyond that in some sense. And often these so-called hybrid functionals. And this is mixing, it's called hybrid to some, one way of thinking about it. You're mixing together a bit of stuff from the wave function, the quantum chemistry community, with density functional theory, which traditionally came a bit more from the physicsy side. And so what I will give a little bit of an outline of, and I'll hopefully include a reasonable number of sort of working examples, or the important bits, about how we can do hybrid functionals in CP2K. They work quite nicely because we've got these Gaussian basis functions, so we can leverage a lot of the know-how from the quantum chemistry community. And there's also another approximation called the auxiliary density matrix method that I'll mention that can give you a dramatic speed up in the hybrid functionals at a cost of a little bit of accuracy, but for many systems I think it's a very worthwhile trade-off. I say this may be a bit small, but if you go to the website and you click on the thing, you can get this, either the interactive slides or the PDF, and you can see them on the screen as we go through. So what are hybrid functionals? Well, if we write down our energy of the system, if we concentrate just on the exchange correlation part, there's underscore C, a correlation part that comes just from our conventional DFT functional. And you can see in the brackets it only depends on rho, the electron density. That was the big advantage of DFT. We threw away all the wave functions, more or less, and just relied on the density of the electrons. And there's this 1 minus alpha, and alpha is this fraction of Hartree-Fock exchange that we're going to put into our hybrid functional. So there's 1 minus alpha, and then there's this exchange part of the conventional DFT. So we'll have it set up like we normally would a GGA calculation, a conventional DFT calculation. We'll have all the correlation energy from the DFT calculation, but we'll have only a fraction of the DFT exchange energy, and what we'll add in, alpha, that's sort of the missing amount of the exchange, will be replaced by the exchange that you would get if you were to calculate Hartree-Fock based on the Kearns-Sham orbitals that we've got. So what actually drove this development of the hybrid functionals? Essentially it was a bit of this joining up of the chemistry and the physics. The DFT is very attractive. We only rely on the electron density rather than the wave functions. It's much simpler. But up until the early to mid 90s, the thermochemistry that we got from the GGA functionals, these ones that just rely on the electron density, was often not good enough to meet sort of the chemical requirements of chemists. They stuck with wave functions. Once these hybrids were started to be used and tested, broadly speaking, they seem to bring some improvements. Better atomization energies, heats of formation. If you go into the solid state, you tend to find lattice constants, surface energies, ionization potentials, band gaps get improved. And I'll talk about this a little bit later. This is something that's sort of attractive to me. If you have electrons that aren't sort of distributed in a sort of typical metal type way in a system, sort of all everywhere, but instead for some reason they like to sit on a site. You think about perhaps iron, you know, you've got these localized d electrons that give you the magnetism. Then conventional density functional theories tend to give a poor job. They tend to spread out the electron rather than allowing it to sit together. So those are sort of practical motivations. Theoretically, I won't go into it, but you can kind of derive some expression based on a so-called adiabatic connection, going from a non-interacting system and turning on an interaction. You can come out with something that should look a little bit like these hybrid functionals. And another argument that I'll try and illustrate a moment is this so-called one electron energy level discontinuity, also known as the self-interaction correction. What you shouldn't have in a system is an electron, if it goes into the system, it shouldn't sort of talk to itself. It shouldn't interact with itself. It should feel the potential from the other electrons. The other electrons should respond to it. One way that this is sort of exhibited is if you could imagine taking a fraction of an electron out of a system. You can show theoretically that what should happen, the energy of the system should change linearly with the amount of electron that you take out up until you've totally removed an electron from the system, at which case there's a sort of shift. And you can relate that to the ionization energy of the system. So there should be an energy level for an electron, and you should take a fraction of the electron out of that level. And the level you should take it from should stay the same, because if you like, the electron isn't interacting until you've completely done it. Then you have a new HOMO, a new highest energy level, and then you shift onto the new branch. So you should have these straight lines between the states with n-1, n plus 1 electrons. And what was observed is that most approximate DFTs are convex, so they go underneath the linear line. This means that it's more energetically favourable to have sort of half electron in a system than it should really be. And this you see it in real systems if you have this possibility, like the localized centers in magnets or whatever I talked about, to have sort of half an electron here and half an electron here. It causes problems with bond breaking, various other things. Hartree-Fock is kind of the opposite. It's this concave function, and it strongly dislikes allowing the electron to have this sort of partial occupancy or whatever. So you tend to get electrons being very strongly localized. So what you can imagine, if you mix sort of a fraction of the red with a fraction of the blue in the right proportions, you'll get a nice straight line, and hopefully you'll kind of get rid of self-interaction error in the system. So going back to the raw numbers, so this, people started looking at thermochemistry over sets of data to try and come up with better density functionals. So one of the earlier ones is so-called G2 set. If you use local density approximation, it's really an actual, okay. So there's a sort of mean absolute error on the various formation energies in the system. They're pretty horrendous. If you go to the canonical GGA semi-local functionals that became very popular in the sort of early to mid 90s, you see that they drop down significantly and they're getting towards numbers that are really rather useful. And then this B3 lip, PBE 0, these give another sort of threefold whatever reduction in accuracy compared to PBE. And this sort of 0.1 EV is getting down to the sort of number that chemists would start to sort of trust for thermochemistry. Still not great, but getting there. And PBE 0 is from the mid-90s, so all of these are going back a long way. There's now a huge zoo. There's many functionals, some over-parameterized, but again, you can start to get these thermochemistry results quite accurate. If we go into the solid state, there's fewer results to look at, but if we look at the band gap of materials, you know, the idea of how, if you're in a bulk solid, from the highest occupied state to so from the valence band up to the conduction band. So the mean error on a local density approximation calculation, so a standard local density functional, they under predict the band gap by about 1 electron volt. Or if you're doing percentage terms across the materials, it's about 50%. So most of the band gaps are underestimated by about 50%, which is not brilliant. PBE, so this GGA, it was in the middle of the previous table. This gives better thermochemistry, but no improvement essentially on band gaps, the positions and the 1 electron levels. TPSS, it's something that includes not just the gradients, but second derivatives of the electron density. Minor improvement, but not really anything significant. Some flavour of this hybrid functional, HSE, another very popular one, underestimates by an order of magnitude less. So we're correcting our 1 electron spectrum. It looks sensible, we're getting band gaps in sensible places. You also get, in many cases, at least for insulators, significant improvement in the ionisation energies and other things as well. So empirically, there's a good argument for it as well. So there are many, well, in many cases they're not totally robust, but there are good theoretical arguments for it as well. Okay, let's actually look at what it looks like in CP2K in a bit more detail. So if we take GGA, the sort of functional that Jörg showed yesterday, so the energy is just a function of the density. So there's this Kohn-Sham kinetic energy, again depending there, the Coulomb interaction, this exchange correlation potential, which is just a function of the density, and an external potential, the pseudo-potentials, any external fields we want to apply. For our hybrid, we replace this exchange correlation just depending on rho with something that depends on rho, so the bit that we had before, but we add in this fraction of Hartree-Fock exchange that depends on psi, our Kohn-Sham wave functions. So what is this Hartree-Fock bit? It depends on the density matrix. So it depends on which of our basis functions are occupied in what proportion in the wave functions. These things, these so-called 2 electron integrals, electron repulsion integrals, ERIs, I'll call it that a few times, it's this integrals, double integral over all space of the coordinates of 2 electrons, and the first electron is the electron, the coordinates appear in 2 of our orbitals or basis functions, and the final thing is the linear combination weighted by how occupied these basis functions are in our guess at the density. The sum kernel, normally this will just be a Coulomb interaction, 1 over r, 1, 2, the distance between the two electrons, and then two other basis functions that are to do with the second electron. So you can see we've got one basis function, two basis functions, 3, 4. They can all be the different basis functions that we are using, so the different Gaussians we use to expand the density matrix. And so naively, there will be, if n is the number of basis functions, n to the 4 of these things that we've got to calculate. If you remember at the end of Marcella's talk, she was showing something that had something pretty nasty with something like 10,000 basis functions. So if you do 10,000 to the power 4, you're getting, we should do a quiz, it's quite a big number anyway. Yeah. We're into sort of trillions and whatever, depending on whether you're American, European, or whatever. Big numbers. That's why these hybrid functions, in a naive way, are rather expensive. They've been not used that often up until relatively recently in the solid state. But there's a lot of things we can do to get rid of these. These electron repulsion integrals, they more or less look like a Coulomb interaction. Yeah, that's not really true. It's an exchange interaction, Coulomb interaction between these things. They're quite local. They drop off relatively quickly, particularly the exchange ones, as these things set away. There's a lot of these integrals that are really going to be rather small and can be neglected. So the next bit I'll go through just a few of the keywords and ideas that are used to chop down the number of integrals that we need to calculate. There's some basic ones. They have sort of permutation symmetry. These interactions don't depend on the ordering of which basis functions which. It just doesn't affect things. So you can get rid of an eighth of the calculations as long as you just sort of order things when you're doing the calculations. So-called Schwarz inequality is almost like the triangle rule from linear algebra. The absolute magnitude of this scalar product type thing, the matrix element of these mu, nu, lambda, sigma is always going to be less than the square root of the magnitude of the what's the word? The mu nu 1 and lambda sigma. So if you calculate these two and they're both small, you know this one's going to be, all of these guys are going to be even smaller, and you can throw a whole bunch of those away. So I'll talk about it a bit later, but this EPS Schwarz is the keyword there that controls it, and it throws away guys that if the magnitude of these is a certain level, then it will throw away all of the mixed terms that are connected with those other ones. And what's important is this scaling from n to the 4 now drops down to n to the 2, which is getting a bit more manageable. And there's a final thing that's done in CP2K, which will actually eventually bring us down to order n scaling, which is to not just use the Schwarz inequality, as we did in the previous one, but to actually look at, so this Pmax, this density matrix element, tells us how much of any of these mu, nu pairs of functions are involved in our occupied space, in our wave functions that are occupied. And so we find the largest value involving any of the pairs of indices that we're interested in any of the pairs of basis functions. We weight that in there. So if the largest element involving any of these pairs of basis functions is very small, essentially these basis functions aren't being used in our description of the electronic structure of the system, and again we can throw things away. So there's this screen on initial P keyword, and this is based on the density matrix at the start of the SCF calculation. So this screening is very efficient as long as you've got a good guess at the density matrix when you start. If, however, your guess is very bad, you may have to redo this or abandon this screening. This is particularly good for molecular dynamics when the configurations are very similar to each other, and also the density matrix is only changing fairly slowly from step to step, so that you always have a good guess at the density. And so if you screen based on that density, you go down to order n. So actually as we go up to large systems, calculating these hybrid functions is not too much of a problem. We can calculate the Kuhn-Sham matrix fairly easily, and again the problem goes back to actually optimizing the density once we've calculated it, assuming we can keep all of these 2 electron integrals in memory. So I mentioned this a bit earlier. I just put in this generalized description of what happens, how these orbitals talk to each other. If we have this thing as just 1 over r, then we've got essentially a standard Coulomb potential. So we get Coulomb interaction and standard exchange integrals. In the gas phase, this is what you want to do. To tell CP2K what this G will be, there's an interaction potential section, potential type inside the interaction potential, which is inside the exchange correlation part. I'll show examples in a minute. There's a trouble, this 1 over r, you may remember when you studied infinite series, something that goes 1 over x, or you've got the power of -1, is difficult. It doesn't converge properly. In 3 dimensions, the same is kind of true. You tend to get problems if we use a naive 1 over r. There's different solutions. One, this HSE that I mentioned earlier, uses a so-called range-separated hybrid. So it's split up into a short range and a long range bit. So there's one bit that's dropping off exponentially, one that's sort of coming back in, and the long range bit is typically replaced by some sort of local functional, and the short range bit can be calculated fairly reliably. So again, you can specify that as potential type. HSE, typically, as it drops off exponentially, it tends to be quite a long range of drop-off. The exponent's quite large, so you tend to need rather large supercells in CP2K to use this HSE functional, but it works nicely. The other option that, well, I mean, there are more, but the other common one is just to truncate this potential. So we just have the full interaction, 1 over r of electrons out till some cutoff distance, RC, and if they're, whilst we're doing the integral, at that point, if they're further away than that, we just throw away that bit of the interaction. This changes the integrals we've got to do from this 1 over r and product of 4 Gaussians. So this 1 over r and product of 4 Gaussians can be done analytically. If we neglect this bit at the end, it's a more complicated integral because it doesn't go from 0 to infinity in the distance, but it's 0 up to some cutoff. And this TCG data contains a sort of numerical stuff about how to do these integrals. So if you introduce this truncated interaction potential, you need CP2K to be able to find this file. In a modern installation, it's in the data and you should just find it and you don't need to worry about that. But if you're using an older one, you may need to copy that across or tell it precisely where it is. Yep. And the snappy name, if we use PBE for this, we've got christened this. What we can do is add in some sort of long-range correction, some approximate density functional based interaction for the bit after the cutoff. But as I'll show at the end, I think probably the best thing is just to have a large truncation radius, and if that's greater than 6, 7, 8 angstroms, then you essentially are making virtually no approximation there. I should say this cutoff radius can't be larger than half of your box size. So if you want to have a large cutoff radius, so sort of something that's pretty close to a full hybrid functional, you'll need a box size that's sort of 12, 14 angstroms in all dimensions. So those are the ingredients for the basic hybrid functional calculations. Should I do the ritual? Has anyone got any questions at this point? Excellent. This stuff is all really nice. It's rather robust. It works well. There's the paper from Manuel and so on from 2008. So we can get down to linear scaling in a large system. The trouble is, as Jörg mentioned yesterday, in CP2K we like to use basis sets, these more-opt ones, with lots and lots of Gaussians in them, lots of primitive Gaussian functions. And this means that even if we're in the n squared regime, we're going to have an awful lot of these 2 electron integrals to calculate. Furthermore, we tend to include Gaussians that decay rather slowly, and that means that this Schwarz screening won't be very efficient until we go to really large sizes. So we're still going to get really huge numbers of these 2 electron integrals to calculate if we just use a more-opt basis set. So there's an example at the end that you can have a play with, that you can see this effect in action. So what was introduced was this auxiliary density matrix method, ADMM. It looks horrible here, but the essential idea, the essential approximation is quite, well, at least in the naivest way of looking at it, it's fairly straightforward. So if I take my Hartree-Fock exchange energy, I can just insert a trivial identity. So let's first include an auxiliary density matrix. I can define it however I like, but what I want it to do is to approximately, in some sense, reproduce my full density matrix. So I'm going to have this auxiliary density matrix, and I P with a hat on it. I'll try and remember to put the hats everywhere, but I may have forgotten some. So I can use a trivial identity here. I can say that the energy, the Hartree-Fock contribution to the energy, which depends on this original full density matrix with the full basis set I was originally using. There it is in here. And I can add and subtract the Hartree-Fock energy I would get if I calculated it using this other density matrix. So I introduce a second set of basis functions, and if I can add and subtract this is always true. This is an identity here. Now if my auxiliary density matrix is reasonably close to the true density matrix in some sense, then let's see what we've got here. So the first thing is the Hartree-Fock energy, exchange energy calculated in our auxiliary density matrix. And then at the end here, I should have coloured this, EX Hartree-Fock P, E Hartree-Fock P hat. It's the difference in the exchange energy between the full density matrix and the auxiliary density matrix. And if these things were close and we had some underlying DFT exchange interaction that was reasonably good, we might think it would do a much better job at calculating the difference in energy between these two density matrices than its ability to get either of them individually. So it's a classic approximation that we think the difference between the Hartree-Fock exchange energies between these two density matrices can be reasonably described by the difference between the DFT exchange energies. So now we only calculate the Hartree-Fock and all these terrible 2-electron integrals using our auxiliary density matrix, our auxiliary basis set, and we do an extra calculation of the GGA exchange energy with our auxiliary density matrix. So if in some sense we can keep these things fairly close, but we can make our auxiliary density matrix smaller, or in practice what we'll do, something that's more amenable to our screening, something where we can use the Schwarz inequality and the screening more efficiently, this is going to work nicely for us. A sort of technical note here. So now the total energy is going to be the energy coming from the full density matrix and the bit coming from that Hartree-Fock energy in the auxiliary density matrix. Using the chain rule and the sort of derivative of the auxiliary density with respect to the full one, we can actually create a Kuhn-Sham matrix that is what we would get from the full one plus this mixed term. So you can actually still express everything as in the normal sort of mechanisms. There's a slight issue about the eigenfunctions of this are not necessarily the same as the full thing. You need some corrections and stuff, but I'll direct you to the paper if you're interested in those details or ask. But the correction is, at least seems to be fairly well defined. So that's okay in principle, but we need some recipe for actually building this auxiliary density matrix. So we're going to build a new set of wave functions which are based on a linear combination of some new basis functions that we've introduced. So some auxiliary Kuhn-Sham orbitals based on these new set of Gaussians. They're always going to be Gaussians. And we build our density matrix from the scalar product of the we sum over the occupied Kuhn-Sham orbitals, that's what this I is, and we take the product of all the wave function, the basis set coefficients for these orbitals. And what we find, we solve for these coefficients so that the difference, the squared difference between these real Kuhn-Sham orbital and the auxiliary Kuhn-Sham orbital is as small as possible. So we just sort of find the best set of these things that look most like the original basis functions. And if we make these guys flexible enough in some sense, we're able to make this fairly small. If we set this ADMM purification method none, this is what it does. It just looks for the best set of these guys in some sense, solves a set of equations, finds those, and that defines our density matrix, auxiliary one. And then that's fed into the 2-electron machinery.
We can do better. We can constrain that our new density matrix will be idempotent, or that essentially the auxiliary cone-sham orbitals are normalized and orthonormal to each other. So there's a set of Lagrangian multipliers. If you do ADMM purification method MO diag in the auxiliary density matrix method, that's what it will do. This method is perhaps a bit more satisfying in the sense that these auxiliary cone-sham orbitals are better behaved. Whether it's actually much more accurate, I don't think we have any firm evidence. There are some other methods, like trying to get the total charge density as close as possible, that you can also do. So there was another paper from the Trodecker group there. I say it's a proper density functional. We can calculate forces, we can do all our normal stuff with it. I won't go through there. There's just some extra terms that come out in the derivatives which come from this, the fact that you've got this second basis function. So it's a little bit of a bookkeeping exercise. It's non-trivial, but it can be done. Yeah. So as I say, we calculate the highest free Fock bit in this auxiliary density matrix, and then there's this correction term, which is the difference of the DFT exchange between the real density matrix and this auxiliary density matrix. In principle, you can use the same density functional that you're using to build the hybrid, but this is just our approximation. You can put in any flavour of density, of semi-local DFT that you like. It doesn't really, in fact, have to be constrained to the one you're using in the underlying hybrid. It just gives us this approximate error term from calculating the exchange using the auxiliary density matrix. So there's an option, exchange correlation func, and and you can choose between sort of Becker, PBE, Optex. There may be a couple of others by now. Does that make a bit of sense to some people, the general idea? We define a second basis set that's smaller, or at least more tractable for that, and within this approximation we can make our number of two electron integrals that we need to calculate a lot smaller. I'll put some numbers up in a minute so you'll realise what a lot smaller means. It is a lot smaller. The good news is that thanks to the original work from Manuel and Jost, and Jörg of course, there are existing auxiliary basis functions that are quite good in some sense for essentially the first 2.5 rows of the periodic table. And then several years later, San Liang and Ben filled in quite a bit more of the periodic table. So I think more or less in the same area where we've got pseudo potentials and Mollopt basis sets, we've also got fairly good quality ADMM basis sets as well. I think that's a correct statement. Anyway, for most elements they are there, so you can just use them. And what's different about these basis sets is that they are essentially uncontracted. So they contain far fewer primitive Gaussians, but they're more flexible in the sense they're uncontracted. They're not all added together with these fixed coefficients to give you a better approximation of the atomic ones. So they're a bit more flexible, so that allows us to fit different primary cone-sham orbitals with fewer functions, and we try and keep them in some sense a bit less diffuse as well. But they're there. If you look inside the data, you'll find them in basis ADMM and basis ADMM Mollopt. So you should find between those two files, for most elements, an auxiliary density matrix, an auxiliary density basis set that you can use. I think these are just some general recommendations about doing hybrid calculations in CP2K. Very general one, check the cutoff, make sure you've got something sensible.
check that you've got sensible properties. I think it's always worth, because even with all this stuff, the hybrid is going to be more expensive. Check your GGA calculation is set up sensibly, you've got a decent cutoff and stuff. That will be, you'll be able to carry that over into the hybrid calculation, and then restart your calculation from a converged GGA calculation with that you've checked that the wave function's okay for that thing and everything is okay. Then introduce your ADMM and check that your ADMM basis is good enough. I think rigid rules in these senses are not very helpful. You need to decide what properties you want to calculate and check that it's not very sensitive to the basis set you're using. At the moment, you can only do this with GPW. You can't use it with the GAPW method that Marcella showed you earlier today, but hopefully that'll be changing soon. And if you want to do fancy things, metals, don't do hybrids with metals, but if you do want to, only this ADMM1, which is the first thing without this constraint that the orbitals are normalized. Right, some numbers. Okay, so if we take diamond, this is about the worst, the hardest example in some senses you could possibly have for hybrid functionals in a sense, because diamond is packed in so tightly that the number of these integrals grows very, very rapidly. But if I do a PBE calculation using the primary basis set, I've forgotten what it is, but quite a good quality basis set, I get a band gap of 4.2 electron volts. If I introduce our auxiliary basis set and do the same calculation, I get 4.4 electron volts. It's not bad, you know, it's not a very good quality basis set, but it's okay. So this auxiliary basis set, it can't just be complete nonsense, it's got to be something fairly reasonable. Because remember we approximated that this auxiliary density matrix is similar in some sense to the primary one. So if now we switch on our hybrid, the number of integrals that I have to do, if I just naively use the primary basis set, is this number. Is anyone willing to read that out for me? I don't know what it is, it's a big number. If anyone tells me how to pronounce it, I'll be very happy. Yeah, big number. If I do the calculation, so this is not ADMM, but I just do the full calculation using the auxiliary basis set, I have this many. So 23.5 billion. Yeah, okay, 23.5 billion. If I look at the band gap I get with the full calculation, it's 6.1 electron volts. If I do it with the auxiliary basis set, it's up to 6.3 electron volts. So it's not disgraceful, but it's not a very good approximation to the full calculation. But if we turn on this auxiliary density matrix method, we can see that the number of integrals we need to calculate is essentially the same as for the calculation just using the auxiliary basis set. So the cost is, broadly speaking, like the auxiliary basis one, but now we're getting an energy gap, band gap, that is a good approximation to the full calculation. And I think that's probably sort of representative of the overall level of accuracy I would expect from the ADMM. Most orbital energies, band gaps, etc., are probably within about 50 MeV of the full calculation if you've got a decent basis set. You may be able to do better, you may be, but it's not perfect, but it's pretty close. And if it avoids calculating, you know, you can do a lot more with this if you're willing to have a small error. I think is often better to do, and I'll show in a minute, a lot more calculations, explore different possibilities than do one heroic calculation. There's certainly a place for the heroic calculation, but maybe not all the time. If we do the same thing for silicon, if I've got this cutoff radius, this bit where I truncated the thing, once you get up to 6 angstroms, 8 angstroms, you're basically converged. The number of integrals is growing, but the screening stops it growing at a horrendous rate. And there is some dependence on the auxiliary basis set. So if I include polarization functions in an auxiliary density matrix, then it makes a moderate agreement. So using a polarizable uncontracted triple zeta auxiliary basis, I get something that's pretty close to the good numbers, and it's a manageable calculation. And this is on sort of 216 atoms. Okay. That's, I wouldn't call it theory, but the sort of background stuff done with. I'll just give a few examples of functionals that are in CP2K, some recipes for them, and I'll just show you a few calculations that we published fairly recently, just to give you a flavour of the sort of systems and the things that you can do using this stuff. And then at the end I'll just mention a few other things that are beyond hybrid functionals. I won't talk in detail, but I'll just introduce a couple of references and ideas there. So you can use this PB0 truncated with a long-range correction, so a bit, GJ bit that's added on beyond the truncation radius. And this other one is this HSE, there's that splitting it up into this long-range and short-range part using a error function, a complementary error function. So if you want to implement those into CP2K, we'll show you how to do this. So in the DFT section, it looks more or less like you've had before. What's a useful thing to know is that you can repeat this basis set file name. So if you've got basis functions in different places, you don't need to sort of concatenate them all together into one file and make your own. You can just tell it to look in basis molopt for the primary basis functions and to look in basis ADMM for the auxiliary basis functions. I've done something fancy, but always restart from a converged GGA calculation or one with a sort of a related hybrid function. And then to turn on the auxiliary density matrix method, so in DFT there's this auxiliary density matrix method, just stick with basis projection unless you know what you're doing. ADMM purification method is either none for the simple one or MO-diag if you want to have these corrections to make it normalized. If a spam call, excellent. I've turned my phone off anyway. So we turn on the ADMM. In the exchange correlation, I'll give you some recipes in a second, but you need to specify the hybrid you'll be using. So how much Hartree-Fock, how much GGA, etc. And the last bit in the subsys section, for each kind, you need to specify not just the primary basis set, but the auxiliary basis set. And if you're using an up-to-date CP2K, you have basis set, auxfit, and the name of the basis function, basis set you want to use. If you are on a legacy CP2K, then instead of basis set auxfit, you see there's a space, they're separated, this is kind of a specifier for the basis set, then you need to use this auxfit base set and then the name of your basis function. but use an up-to-date version of CP2K and then we don't get into this. And specifying the exchange correlation functional. It's a little bit ugly, but they're recipes, you know, you use it once, as long as you understand. The only things you'll actually be tweaking will be how much of the GGA exchange, the truncation radius, and how much of the Hartree-Fock potential amount to be using. There are some shortcuts, but I would tend to recommend specifying stuff, finding a one that explicitly specifies things, because I'm never quite sure what's going on with the shortcuts. Have we done anything about? No. So we've got the exchange correlation functional. This is PBE 0, so I've got the original PBE. I'm going to have 100% of the correlation. So if you remember, I had the full DFT correlation, but I'll only have 25% of the PBE exchange. I can include the long-range correction if I like. This is kind of optional. So this is this long-range correction. And that specifies my GGA part of the calculation. And then there's a Hartree-Fock bit where I tell it about the Hartree-Fock part of the calculation. And what we have here, we've got the screening section, so this EPS Schwarz. 10 to the minus 6 is quite aggressive, but is often okay for anything. 10 to the minus 7 is perhaps a more sort of conservative starting point. Screen on initial P, so you don't really want false in most cases. If you've got a reasonably good density matrix, make that true. So the potential type, truncated, cutoff radius, you probably want 6, 7 or 8. You may or may not need to specify where this file is. It should just be found in a modern version. Fraction of the Hartree-Fock, 0.25, so it's 25% Hartree-Fock exchange and 0.75, 75% PBE exchange. So those want to match. So probably what you'll be wanting to change for this recipe would be the cutoff radius, the fraction of Hartree-Fock, the fraction of GGA exchange. There's this magic keyword EPS storage scaling. I won't go into it, include that. It just compresses the integrals a bit so they take up less space. And max memory, you want this to be essentially as large as you can afford. So this is per MPI process, and this is about 2.5 gigs. So it depends. I don't know what the setup is on the machines you've got available. I don't know how much memory is per box, but per MPI process, it's probably going to be of that order of magnitude. 1.5 gigs, 2.5 gigs. Maybe lucky and you can push it further. And there's an equivalent recipe for HSE, and it includes this long-range PBE, this complementary error function with these parameters. Again, you can check it. And instead of the truncated potential, it's got this short-range potential here.
About 5 gigs per core.
Okay, so if you're running on here, you can probably push this up to sort of 4,500 or something like that if you need to leave enough room for the operating system and the GGA calculation. So this is the amount of memory used for the Hartree-Fock bit. And this is the really important thing, and where CP2K really wins, is we calculate all of these 2 electron integrals. They're kind of geometric things, yeah? They're a basis function, how far apart they are. And so they only depend, if you like, on the geometry of the atoms. So when we're doing an SCF cycle to find the best density matrix, and we're going through to find convergence, the integrals aren't changing. So if you've got enough memory, we can calculate them all up front, store them in there, instead of having to calculate them or get them from a disk, which is even worse these days, we can keep them in core. So here's an example. If you've got medium print level, so it's probably worth doing that for this. You can see the number of Cartesian primitive electron repulsion integrals calculated. big number. But the important one, number of these stored in core. So we calculated a lot, but only 1 in 10 was actually needed in the end. And then the number of EOIs stored on disk and the number calculated on the fly. Ideally, these want to be 0. This means you've got all of the 2 electron integrals stored in the thing. So that means when you're going through the later cycles, you don't need to recalculate them. And what you should see, if that's true, well, this is perhaps not a very good system, that the first step will take quite a while because you've got to calculate all these integrals. But the later ones, after the first one, they should cost not much more than a normal GGA calculation because you've already got them all there. So that's a big, big speed up if you can get to that point. Again, I won't go into it. This may be another place where you want to use this PSMP executable, this mixed MPI and OpenMP parallelization, because then you can share memory and get a bit more out of it that way. But the easiest thing is just to throw more processors at it until you get it in memory. Yeah, so you need this libint library. It can be, you can use the toolchain to include it. It is a little bit fiddly. There's a couple of gotchas in terms of C versus Fortran numbering. Yeah, you want to keep everything in memory, and you may want to try these hybrid things. Are there any questions on the mechanics of doing stuff? Yeah, consistent at any rate. I'll mention a couple of things that we've done, just show off a few calculations, give you a bit of a flavour for a few extra things you could possibly do as well, and then I'll sort of round up there. So, this was something from a couple of years ago. We had some experimental colleagues. Again, it was STM measurements, a little bit like what Marcello was talking about. So they took rutile titanium dioxide. We always claim it's got something to do with solar materials and sunscreen or stuff like that. It's used a lot, catalytic material. What was interesting, so rutile, why it's used in solar cells, it's got a band gap of about 3 electron volts, broadly speaking. So it's a semiconductor. But what they came up with was a scheme to really heavily dope the bulk but leave the surface more or less pristine. And what this meant was this material stayed conductive down to about 4 Kelvin, which is kind of quite cool. No one had managed to get that low before. And they had this STM, so they could come in, it was still conductive at 4K, they can make the measurements. And what is known about titanium, rutile, is that you get these localized electrons, so-called polarons. So you have an electron in a metal, they just whiz around, they're delocalized. So it's this thing I talked about right at the beginning about whether the electron likes to be localized or delocalized. In rutile, they couple to lattice modes, to phonons, and they tend to localize. And so if I look at a side shot through the surface, if I've got 2 electron polarons, they sit in these subsurface sites in essentially d orbitals of titanium, this TiO2. And if I sort of look down and plot out essentially this Tersov-Hammond STM image, or just take an isosurface of the charge density of the field states, I can see these guys here. And so if I have an oxygen vacancy, if I remove an O2 minus, I leave 2 electrons behind, and they sit on these lattice sites, and I can see electron density associated with those in the field states. And I can put them together, or here, or I can start to move them apart. And this I found to be the most stable configuration for the 2 electrons around the vacancy. but there's another one very close, a little bit further, or whatever. And so experimentally, they have a recipe for making these vacancies. They can mess up the material and kick off these oxygen vacancies. I won't do it. If anyone wants, I can show you, they've got real-time videos of doing this, but essentially they can bash oxygens off the surface and then they can actually push them around on the surface as well. So what they can do is make not just an isolated oxygen vacancy, but they can also make trimers, tetramers. They can push these oxygen vacancies together, and they should have these electrons distributed around this vacancy. At least that's the sort of the common thing. So as these are experimental images here, these are empty states, filled states. They can form two oxygen vacancies together, which should have 4 electrons around them, and then a trimer, different types of trimer, tetramer. And so the oxygen vacancies in the tetramer, they're all about, I don't know, 2.5 angstroms across. So that means that this bit of the central image is something like 1.5 nanometers in length. So to fit it into the supercell to do the calculations, we've got to have a 25 angstrom by 25 angstrom box, and getting on for 1,000 atoms there with transition metals and all sorts of nastiness. And we can do that. We can get simulated STM images that compare quite favourably with the experimental stuff. And they can also see these locations of these polarons on the surface, and they can make the measurements at 20 Kelvin, 15 Kelvin, 7, 4, and they can actually see these polarons getting trapped in on particular lattice sites. That was quite nice. One more thing I want to show, it's not so much huge systems, though they are quite large, is just the fact that because these calculations are relatively tractable, we can scan over the sort of parameters we're using in our hybrid functional, how much exact exchange, and so on. We can do it fairly systematically and see what the behaviour of the system is. So more titanium dioxide. It makes not just this rutile stuff, but there's anatase, brookite, and these more exotic ones. You can see they're all sort of essentially edge or corner sharing octahedra, so they've all got that sort of structural element, but you can bung it together in different ways. And you'll get oxygen vacancies or sites where holes can sit on these things. And so there's a whole bunch of similar but chemically distinct environments that these electrons could want to sit. And what we wanted to find out was whether one density functional hybrid would give a decent description of all these materials. Did I bring in? Yeah, I didn't bring it in. So this self-interaction error or whatever in a material, you can show theoretically that the energy to ionize a system using density functional should be equal to the highest occupied Kuhn-Sham orbital. So if I do the calculation and look at the highest energy orbital in the system, I'm going to call that orange, and there. The other thing I can do, the other way I can calculate the ionization energy of the system, is to calculate the system with n+1 electrons and subtract the energy with the system with n electrons in it, take the energy difference, and that again is the ionization energy of the n+1 system. And so if everything is working correctly, so for the exact DFT, this orange line, the energy of the highest occupied state, should be equal to this ionization potential I calculate with the geometry fixed of
the two different systems with an extra electron or not in it. And what we could do, we took PBE 0 and we could vary the amount of exact exchange in the system. On this green one, actually, I've got the band gap as well as a function of the exact exchange. So as I say, if everything's working correctly for an exact, this is a condition on the exact density functional, this blue line and this orange line, that they should give us the same value. So if I take annotates and I scan across this value, we see that there's a distinct difference between the 1 electron value and the actual many electron ionisation energy. And as we're getting towards the point where they start to line up, actually the polaron delocalises. If you remember this bit about the convex and concave, other way around, that as we reduce the amount of Hartree-Fock, the GGA likes to spread out the electron. So rather than get it sat on one site, it just sort of splurges out all over the pit with stuff, and you can't really do the calculation. In rutile, as we come in down from about 20% Hartree-Fock, it's actually almost flat, and any value here actually gives a good agreement between the single particle and the full calculation of the ionisation energy. This is kind of also true of the annotate's whole polaron. So this is, instead of an extra electron, it's the whole that's missing. And we consistently get that a rutile polaron can't be localised. Doesn't like it. We've got to put in a lot of exact exchange to get it to localise, and we don't get this agreement between the two lines. And experimentally, these two things are somewhat dubious, whereas these are quite well known, so that all sort of fits in. And we could do a similar sort of game for these. So this is the annotates and rutile. This is what the electron localised looks like. This is the whole, actually, and that's the electron. And then in these more exotic materials, you can actually get these sort of coupled and sort of molecular ones. It's some quite interesting ones. But the bottom line is that we can find the range of values for the different sites and the different holes, different electrons in the material as a function of the fraction of exact exchange. And so what we're plotting is the range of values where this condition that the single particle and the ionisation potential calculated from the whole system are in agreement. And round about 11.5% exact exchange, it fits almost every defect that we considered, every polaron, hole or electron in these 5 different phases of titanium are all reasonably described by this functional. And so we can draw these charge transition levels for these defect energies. And so this is of interest when you're doing the solar stuff, where electrons and holes sit. If you can control that, you can start to do photocatalysis or do useful things. So we can indeed find a sort of a fairly good functional for everyone. And as you can see, I mean, that's what I didn't emphasise, is that the localisation is also a function of the lattice. You need the lattice to move to get the things. So you need to do a full geometry optimisation at each of these fractions that Razak did. And so this is quite a lot of calculations here. And we could do those relatively readily in CP2K. We would have burnt a lot of CPU time doing it in another code, scanning through these stuff. So it's a nice thing. I've got 2 more slides with stuff. Any questions on that bit of stuff before I do the last couple? Just to say, in principle, this is sort of a bit advanced, you can do quite a lot of things using ADMM. There was a paper we did a while back. We had magnesium oxide and insulator on top of metal, and we put an ADMM basis on the magnesium oxide, but not on the silver. So we had sort of a GGA calculation of the substrate and a hybrid calculation of the stuff grown on top. And that worked okay. There's some issues with it. So that's a bit of flexibility. And in principle, you can even go and do something a bit like plus U that I've not mentioned. It's another way of controlling the self-interaction error, but in specific orbitals of a material. And so you can in principle just put it on the d orbitals of titanium atoms or something if you like that. And that will give you far fewer 2 electron integrals to calculate, and it will be really quite cheap and efficient stuff that can be used. I could go on and talk a lot more about going beyond hybrid functionals, and CP2K has also got quite a lot of facility in beyond Hartree-Fock wave function theory. But I thought I would leave that up to you to read around and ask about what you're interested in. So the hybrid functionals, it's a 2 electron thing weighted by the occupied density matrix. So we use information about the occupied orbitals. We could make a more flexible functional if we included information also from the unoccupied states. And there are recipes for doing that using so-called double hybrids, which mix MP2 and Hartree-Fock together with GGA. RPA you could put in that thing. There's an exercise, a set of things that you can do here, looking at setting up the hybrid ADMM calculations. I know that this was prepared for a slightly old version of CP2K, so that you need to change the syntax for specifying the basis sets. So it's a good test that you can find it in the input file and make the change. If you're interested in post-Hartree-Fock stuff, there's MP2 exercises, GW exercises here, and talks on MP2 and GW from previous workshops and stuff. You can go into a lot of detail. San Liang made these extra ADMM basis sets, and frankly I've nicked quite a lot of his slides. I've reformatted them and stuff, but I acknowledge I've stolen. The original ones you can find here. They might be useful. They also contain quite a lot of details, not just about the hybrids, but about dispersion corrected functionals and using plus U. So they've got recipes for the different Grimmer corrections and stuff in them, I think. And I should always thank all the CP2K developers for lots of interesting stuff over the years. So I think that's all I wanted to say to you. Have you got anything to say to me?
Any questions?
Any questions? The main thing is to have a play around and decide what you want to do. We'll be around.